Good evening, everyone. Again, welcome to another presentation on the Perspective series. I'm Michael Glore. I'm the Interpretive Operations Manager at Olympic National Park. And if you've participated in Perspectives before, you're probably more accustomed to seeing one of my coworkers, Dean Butterworth, who's the park's outreach and education specialist moderating this. But unfortunately, Dean has some conflicts this evening, but it's my pleasure and honor to be with you. Before we get started and I hand it over, I want to again thank Gina and the North Olympic Library System for making this series possible, as well as the Friends of Olympic National Park and Discover Northwest for their support, and to all of you for being here. As Gina also mentioned, I'll be monitoring the chat for questions. If you have any questions, feel free to drop them in the chat. We'll save those till the end. And however much time we have available, I'll try to ask them all of our presenter at the very end. So be sure to keep those coming. And again, with that, I thank you all for being here. And again, remind you to please now turn off your cameras as I hand this over to our distinguished guest speaker for this evening. Kathy Goetz Troost is a teaching professor at University of Washington and a senior consultant for S&W Incorporated, both in Seattle. She's been working as an engineer and geologist for 43 years and has worked for both the public and private sectors. She started her career in the Midwest, then moved to Fairbanks, Alaska to work for 5 years. And for the last 37 years, she has focused primarily on the geology of the Pacific Northwest. Kathy has produced many geological maps and papers about geologic hazards in the Pacific Northwest. At the University of Washington, she has been working with graduate students, preparing them to enter the workforce and helping them to use robust scientific reasoning to address problems in the natural and built environments. She has convened many workshops and led many field trips for her peers and with the public. And most recently, Dr. Troost has been leading some research efforts in the Forks and Rialto Beach areas with her graduate students. So Dr. Troost, welcome. Thank you. And the Zoom is now yours.
Great. Thanks for the introduction, Michael, and welcome to everyone. So I am now going to share my screen, so bear with me for a moment. And let's make sure this is working. Okay, Michael, could you let me know if you just see a single slide at the moment?
I do. Geologic Mysteries of Rialto Beach.
Awesome. Okay. All right, so I want to talk to you about this area that we've been working in for quite some time now. Just one moment. Let me get my bearings here with everything. We've been working out at Rialto Beach for several years now. And this is what I'm going to present to you is a collaboration of the research of several graduate students and myself. And just as Gina shared with us, I also would like to acknowledge that we are working here on this research project on the ancestral lands of the Lapush and Quileute nations. I mentioned that this has been a collaborative effort, and here you can see many of my co-authors as well as colleagues that I've been working with for several years on this project. They have made it a lot of fun to be able to work out there with this group of people. And even after the students finish their research project, they still like to carry on and stay involved and help the new graduate students work out at Rialto Beach. It's such a fascinating area and such a wonderful place to be. So here's a roadmap about what I'm going to talk about tonight. I already introduced who has been involved with this. I'm going to tell you a little bit about where Rialto is in case you don't know, why we're working out there, tell you a little bit about the background, and then go into some details about what we're doing and how we're doing it. And then when some of these events and activities have occurred in the geologic past. So here on the right, you can see location of Forks in the northwest part of the Olympic Peninsula. And then on the left-hand image, with this arrow is pointing to the Rialto Beach area. just north of the mouth of the Quileute River and west of Forks. A couple of things that I want to point out to you with this map are that when I talk about Rialto Beach, I'm talking about this stretch of coastline here within the Olympic National Park. And again, here's the Quileute River. The village of La Push is here at the mouth. There's a jetty in this position here, a natural spit that has been armored. Hole in the wall, for those of you that have walked out there, is about here. And the other thing I want to point out is that the net shore drift, in other words, the direction that the sediment moves most of the time, is to the north, which tells us prevailing winds, prevailing waves are pushing sediment generally to the north. I also want to just acquaint you with the sort of the landforms out there. So when I'm throwing these words around, you'll know just what I'm talking about. So I've captured a couple of images from Google Earth and turned them so north is not pointing up, just so that we can look at this area in perspective. So the upland is here, some 400 feet above sea level. Here's the mouth of the Quileute coming out to the Pacific Ocean. Here's the jetty, and then this is Rialto Beach. The other things I want to point out are this slope along here, which is a sea cliff, a former sea cliff. And out in front of that sea cliff is this surface right along here that's gray. You can see it here at the parking lot at Rialto Beach, and you can see it in between the dying trees along here. That's a low elevation terrace that stands anywhere from 1 to 3 meters tall. So why are we studying Rialto Beach? I mentioned this low elevation marine terrace. We're intrigued by that. In fact, John Riedel with the National North Cascades Park got us interested in this. He and Ian Miller both were speculating about what the origin of this could be. And we'll talk about that the rest of our time today or this evening. So what's the origin of that terrace? And why are the erosion rates out there so high, or why do they appear to be so high? So we're standing here on that former sea cliff in the more heavily forested part of the slope. And the terrace is this surface out here in front. And you'll notice the trees on this terrace are not very healthy, right? And then on the right-hand image over here, we also see the front edge of the terrace, where the terrace is the highest, and we see how it's failing and how it's being eroded. Chunks and blocks are falling off and being carried away in the waves. So we have to look at a whole lot of different clues, try to put a whole bunch of puzzle pieces together to try to figure out, why is that terrace there? And why does it seem to be eroding so quickly? So we've approached this by thinking about erosion, landslides, and climate change. And we're trying to piece all those things together and ultimately wanting to know, did uplift occur out there? And I'll explain that a little bit later. There are a lot of possibilities to explain how this terrace came about. This image here on the right, you can see the terrace here highlighted in tan. It's this nice, relatively flat, fairly narrow surface at the base of this former sea cliff. And this is the upland up here on top. And we're looking at a LiDAR image that shows us the topography underneath the vegetation. That's what this image is. So what could be causing the things that we see out there at Rialto? One idea is that there's been an abrupt, sudden, relative sea level change. Either the land went up or sea level dropped. In either case, a relative change. Or maybe it's a result of long-term erosion due to long-term sea level rise. Perhaps there's a component of sediment supply changes. I mentioned there's a jetty to the south here. Has that had an impact on nourishment of this beach? Have landslides contributed to changes in the sediment supply? We also know that the parts of the Olympic peninsula are undergoing long-term uplift because of tectonic compression. So could that be part of the story? Is there an increase in storminess? And by storminess, I mean, are we seeing more frequent, more intense storms? Or, and what's likely, is that it's some combination of these things that I mentioned. So a bit of background will help set the stage. And it also explains sort of why this is such a fascinating and exciting place to work. The area has been glaciated. It has been impacted by many earthquakes, many landslides, extensive erosion. There have been major windstorms out there, flooding. In other words, this is an incredibly dynamic coastal environment. And on the right is just an image of Blue Glacier from Mount Olympus as a reminder that this area has been glaciated by two major types of glaciation. So I'll take a minute and describe this map because it's pretty complex. So here's the state of Washington here and Seattle. And we see things in purple and white and then blue and sort of light blue, right? So this is water. And what this map is showing us is the maximum extent of previous glaciations. The Cordilleran ice sheet, which advanced down from the coast ranges down into the Puget Lowland and across eastern Washington and into Montana, extended down into the Puget Lowland via the Puget Lobe. But there was a lobe that went out the Strait of Juan de Fuca, and we call that the Juan de Fuca lobe. And if you look at that boundary, it hits right here at the star, which is right at Rialto. So we know Rialto has been impacted by what we call continental glaciation, and that's happened, gosh, at least a dozen times or more. Now, if we look at this purple, this is showing us the extent of alpine glaciers, like the Blue Glacier, but at a time when climate was cooler, those glaciers extended down the mountains, down the rivers, down the Hoh, down the Bogachiel, etc., out to the coast. And we also know that that occurred in the Rialto Beach area. The other interesting thing about this map is this line here is the modern shoreline. But when we had glaciers in the area, sea level was lower and the shoreline was much further offshore. So sediments used to extend quite a bit further offshore than they do today. The other thing that we show on here is this red line, which is a projection of the edge of the Cascadia subduction zone. And I'll tell you about that next. It's an area where oceanic plates are subducting under continental plates, right? And that zone where they are slipping is the source of large subduction zone earthquakes when that slip occurs. The last one to occur along the Cascadia subduction zone was in 1700. And there are other types of earthquake sources in our region, but this is the one that has mostly affected the outer coast areas. These are capable, this earthquake source is capable of producing magnitude 9 earthquakes. If we look at land records, it appears that there have been 7 to 8 of these big earthquakes in the last 3,500 years. If we look at records offshore, we can extend the record back to 10,000 years and estimate maybe 23. So it's not totally resolved what that recurrence interval is. However, most of the scientists agree that we can expect to see one of these large subduction zone earthquakes every 300 to 500 years. This is the main driver for us working out at Rialto, and I'll get back to that in a moment. I mentioned that it's a very dynamic environment. We love working out there. Every time we go out there, we see something different. Ian Miller here, one of our collaborators, has been working out there for many years now, over 10 years now. And he goes out and measures transects perpendicular to the beach. And these are pictures here from the same location along one of his transects. And what you can see in August 2019 is the edge of the terrace up here with no woody debris in front of it. But in December 21, look at this large wood. This wood is incredibly mobile out there at the beach. And you've been out there, you see how big some of these trees are with the root wad still attached in some cases. This chart that he put together is a monthly chart for 7 different transects. And it tells us how many pieces of wood his transect crossed each month. So for example, in June of 2019, he saw 4 pieces of wood. A month later, 0. A month later, 3. A month later, 0. A month later, 8. You get the picture. This is telling us that this wood is very mobile. And we understand that because there's such a dynamic wave environment out there. The image on the upper right is from Lonnie Archibald from one of his books in 1986. And it shows waves cresting over part of the jetty out by James Island. And the jetty is there to try to prevent erosion and prevent this dynamic environment from encroaching on critical facilities and villages. And on the bottom right is a tamer picture, and it shows us this gray area here behind some of the students. And that gray area is gravel that's part of the modern beach deposit that gets moved around during with waves. And then over here behind this black circle, you see this sort of rusty brown color of sand and gravel. This is also beach deposits, but we've interpreted these as being older beach deposits and with modern beach deposits out in front of them. This is the front edge of this terrace that I'm talking about. And this here is the terrace surface. So the modern waves throw modern beach deposits up onto the terrace, but the terrace itself consists largely of these old beach deposits that are now up higher than most of the modern beach deposits, beach material. So with that background, I want to start talking about some of the elements that we're really trying to understand better. And one is erosion. How are we determining how much erosion is happening and what kind of erosion is happening? So we've come up with a suite of techniques that we use to try to understand whether or not the rate of erosion is increasing and if that's changed over time. I mentioned that Ian Miller is surveying the active beach, and I'll show you an image of that in a moment. We're monitoring trees and looking at how close they are to the edge of the terrace and looking for changes in that distance. We're evaluating landslides and debris flows and trying to date those occurrences. We're also dating deposits in trees to try to get a better understanding of the age of the landforms. We're mapping those former beach deposits that I showed you, and then using various types of photogrammetry techniques and modeling to analyze the position of former shorelines. So this suite is getting at both short and long-term erosion, but none of it's getting us back to really long-term in a geologic sense. And I'll explain that as well in just a moment. Here we see Ian Miller on the left with his GPS unit, and he occupies a set of transects every quarter or so, and he's been doing that since 2013. So he walks along the transect and determines the elevation of the beach surface. And on the right, you can see all of these lines are some of the transects that he goes out and monitors. When he's out there, he also takes pictures of the beach so he can see how the grain size changes, which tells him something about how much energy is entering the beach environment. So now this is a complicated figure, but we don't have to delve into too many details. This is also from Ian Miller. So along just one of his transects, and here it is, this red one, this red line here, he's measured that beach surface, the elevation of the beach surface, over this 12-year time period here. And he can plot those surface profiles together and see if there are any trends, and see if there are any changes. And what you can see in this image is that the youngest measurements, which are black, blue, green, and the yellows, are fairly high on this chart. And then the more recent measurements in the oranges and dark reds are a little bit lower. And so what he's showing at this location is a trend of the surface of the beach dropping over time. And that is depicted in this chart down here on the lower right. But you'll notice, look at all the noise. These are the data points, right? It's a general trend. It's not a linear trend because there's so much variation because of how dynamic the environment is. When he does the same sort of graphics for these other transects, he sees different things. So what that's telling us is it's a very complex system, and we're trying really hard to understand it. So I mentioned that we are using the trees as benchmarks, basically, to try to look at short-term erosion rates. And we noticed this totally by accident, came across this technique by accident. In June 2018, we saw this tree at the edge of this terrace location. We call this Terrace Site 3. And this tree here, which we named Jack, is standing upright. A year later, Jack is tipping over, and we notice that there's some erosion around the roots of Jack. And that was in July. By October, Ian Miller had reported to us that Jack had tumbled over. And here's the root wad from Jack. And here's the edge of the terrace. You can see how close together they are. But we started monitoring the gap at Jack over time. This gap is widening over time. And by looking at this width change, keep in mind these pictures are different scales, so you can't really compare the yellow bars. We've estimated that the amount of erosion that's happening at the front edge of the terrace here is on the order of 1 to 3 meters per year. So almost 10 feet per year. Now, this is not to say that every year it's eroding 10 feet, but on average, some years are eroding more and some years are eroding less. So this is one of the ways that we're using the trees to help us look at erosion rates and trying to decide if those erosion rates are increasing. Because if they're increasing, then this becomes something that we need to be aware of. So we've got about 14 trees now that we're monitoring, and they're in different positions on the landscape, as you can see here. And we routinely measure from the base of the tree to the front edge of the terrace, and we can tell how much erosion has taken place. That's been a really fun effort. And we've already seen some significant changes in just the few years that we've been out there. So for example, this is Boris, and next to Boris is Vespa. Boris was first identified by Mary Alice Benson, one of my colleagues here, because this tree is standing up on the beach face all by itself, and there are no trees around it. And we tried digging down to the bottom of it and try to figure out what was going on, but it just seemed like a very serious enigma to us. We were speculating, how did Boris get there? Did it ride down on a landslide down this slope? Did the forest used to extend all the way out here and the forest edge has eroded back to the position it's at today? Or did waves push it upright? I mean, we have to think about all of these considerations. We've actually been able to use Boris back through time a little bit. I was able to get coordinates, GPS coordinates for Boris's position, and then look at old photos and track Boris through time. These images, the two on the leftmost side, are from the Ecology Shoreline Viewer, oblique photos of all the shorelines in Washington. And here's Boris in 2006. And Boris is right at the edge of the forest. In 2016, you can see wood piled up behind Boris, and there's a little more separation between Boris and the edge of the forest. And then in 2021, we see this much larger gap here. So if we say that Boris is in the place where it grew and the edge of the forest has eroded, then we can say since 2006, X amount of erosion has occurred. When we do that, we come up with something like 5 meters per year, 25 feet per year. That's pretty extreme. We don't really believe it, but at least it gives us maybe an outer limit to what we can say about Boris. So we're continuing to study Boris and try to understand if this tree can be used to monitor erosion. Interestingly, back in February this year, there was a big storm, and the tree that we had identified to the left of Boris fell down. Vespa fell and actually hit Boris, and we thought, well, this is the end of Boris. But Boris survived. However, I just got word in November that Boris might be gone. I don't know. We're going to have to go out there and document, but it's possible that we no longer have Boris to help us monitor changes. Are there other trees like Boris that have been on the beach? I think so. In fact, here's an image from Lonnie Archibald of a tree stump sitting on the beach at Rialto. So if we can identify other trees like this, we might be able to look at other estimates of erosion over time. However, just when we were getting excited about using these trees, we found this. This is a stump that appeared in between one of our visits. It was not at this position before. It's standing upright as if it grew in place, but it clearly did not grow in place. So it seems clear that at least in some cases, waves can turn stumps upright, but I'm just not sure how big a tree waves could do that to. So stay tuned. We're going to try to get that resolved. So we're seeing this erosion out at Rialto, and we have to think about what could be causing the erosion. Is it a natural process related to sea level rise, or is something else going on? And so we had to address the potential impacts of the armoring of this spit and the dredging of the channel. Now, let me say that this is a vital navigation channel here. There's an important Coast Guard station over here. The village of La Push is here. The fishing boats are here. So this is an important structure, but it appears to have interrupted the flow of sediment from the mouth of the Quileute out to the beach environment. And during floods in the past, the river would breach the natural spit that was here and send sediment out here to the Rialto Beach area. That's not happening anymore, thanks to these big riprap rocks that are now placed along the jetty. But one thing that is happening is the Corps of Engineers is periodically dredging this channel, and some of those dredge spoils are placed out here on the outside of the jetty. So some nourishment is happening, but is it as much as used to happen naturally? is the question. So a student named Monica Hill just finished this part, this study, where she analyzed former shoreline positions over time by collecting historical imagery and maps. And she was able to go back as far as 1887. This map happens to show the mouth of the Quileute exiting through that natural sand spit that used to exist. And periodically, shore drift would bury this opening, and periodically flooding of the river would open this opening back up. But in 1952, or sorry, in the later 50s, the Corps of Engineers started armoring the spit to prevent this breaching from happening, to protect this critical infrastructure here. And so this is more what the scenario looks like today. So what Monica Hill did was map out the shorelines on 22 different maps and photos, spanning a period of 130 years. So in 1887, the shoreline and the oldest shorelines are shown in green, and the youngest shorelines are shown in red, and there's a gradient of color. And so what we can see happening here at Rialto Beach is the shoreline used to be further offshore, and it has steadily moved inland to its current position. The opposite is actually happening at First Beach down by La Push, where we see the oldest shorelines inland and the newest shorelines seaward. So some interesting trends that she found, but she found that this has been going on for over 100 years. And this image summarizes that, where we have curves to the left. The beach is reducing, being eroded, and where we show curves to the right, we show accretion. The beach's sediment is being added to the beach. And her average, again, averaging every year and not looking at sort of the highest and lowest values, she estimated about 0.8 meters per year of erosion along Rialto Beach. So similar to some of the values that Ian Miller has found. But we also know that these rates have varied over time. And this doesn't really answer our question of, are the rates increasing, which is the sense that people have when they go out to the northern corner of the Olympic Peninsula. So Monica looked at the patterns in blocks of time. So she looked from 1887 to the mid-1950s. And each one of these little lines represents where she measured the position of the shoreline. And so she did a really robust study looking at these old air photos and maps over this time period. The red colors are erosion. The blue colors are accretion, where the beach is building up. And what we see here along Rialto Beach is largely these warm colors, the oranges and the reds, that indicate that in the early part of the 1900s, up until the middle of the 1900s, this was a beach that was eroding, and it has been eroding for a very long time. The next time period that she looked at, and these time periods reflect both the history of armoring of the jetty and the data that was available to look at. What we see in this time interval, this 40 to 50 year period, is even more erosion along the Rialto Beach area. And so this is after the jetty was enhanced so that breaching didn't occur as frequently. So more erosion here. And then the next thing Monica did was, well, let's look at what the really short time period looks like. And so she looked at 2011 to 2019. And if you look at the color patterns, they are all over the place, right? So there's even a little bit of accretion showing up here. and quite a wide range in the amount of erosion that's happening. This is very consistent with what Ian Miller has been finding by actually going out and measuring the beach surface itself. So it's a complex story. Overall, long-term erosion. It isn't just because the jetty is here, but it has been happening for a long period of time. So let me summarize all of this erosion information that we've come up with. We've got anecdotal information. Jill Silver has been going out to that beach over a 50-year time period and noticed that, well, for longer than that, but her observations have been that the forest edge has retreated something like a meter, half a meter to a meter per year over that time interval. The repeated GPS surveys that Ian Miller is doing, at least for one stretch, also is in agreement with those numbers, something like a meter per year in the area that we've been studying, this Terrace Site 3. The work that Monica Hill did shows a range of a half a meter to 2 meters per year. Looking at the gap at Jack, the tree that fell over, we're seeing 3 meters per year, and that's a very short time period. And then Boris, the tree that's standing out there on the beach by itself, maybe as much as 5 meters per year. So that's a huge range, actually. And probably what's more realistic is something on the order of 1 to 2 meters per year on average erosion. But it does appear that the rate is somewhat increasing over time. So another part of what we're doing out there is looking at landslides, in particular, what kinds of landslides, how often do they happen, and what's triggering the landslides. And the underlying question we have, of course, is whether or not the earthquake that occurred in 1700 along the Cascadia subduction zone, if that triggered landslides. And so far, no one has found any evidence of landslides that can be correlated to that particular earthquake. Although we suspect they're out there, we just haven't seen them yet. We also may be able to address that question, we're thinking. So here's the LiDAR image again, and each one of these red arcs shows us the top edge of a landslide. So there are many landslides above the beach. And then coming out of each of these steep ravines are debris flows. Here's the terrace. You can see that surface all along here. And these stars indicate where we have been concentrating our chronology efforts, where we've been concentrating our radiocarbon dating efforts. And you've heard me mention Terrace Site 3, that's this location here, which corresponds to the heart of this landslide. So we've been working on the landslides for a bit, and Elise and Chelsea and Caitlin have all been working on the landslides out here. So I want to show you some of the work that Chelsea Bush did. She was the first one to start working on landslides out there, and she wanted to see if she could use dendrochronology, dating the trees, to determine the age of a landslide. And she was focusing on this landslide right here. And so she cored something like 22 trees with increment borers, and she cored Sitka spruce trees of variable diameter all over the landscape, from the terrace all the way up to and on top of the upland. And she found that all the trees she cored were younger than 100 years, which was a bit challenging because they were of variable diameter. And normally we like to think that the diameter of the tree tells us something about the age of the tree. And we thought we could develop a growth curve that we could use to date landslides. But as it turns out, that didn't work out here. And one of the reasons it didn't work out here is because of this great Olympic blowdown that occurred in 1921. She found this information in some old newspaper accounts. Here, the Forks Forum. There's a person for scale, but this image shows you just what some of this tree fall looked like following this blowdown. Something, you know, like several billion board feet of timber was lost during this blowdown. Gusts down around the Columbia River reached about 180 miles per hour. And near Grace Harbor, about 140 miles per hour. Up here in the Forks area, it was, the winds weren't quite as strong, but this estimate from the ONRC GIS group found that in the area that we've been studying, something like 30 to 40% of the trees were blown down in 1921. And so that explains why the trees that we looked at were all younger than 1921. All right, so in order to continue trying to understand the frequency of landslides out there, we've been looking at the deposits in the terrace because landslide deposits have come down and accumulated on the terrace and buried these older beach deposits that I pointed out earlier. The image here in the middle shows us a stack, you can see the layers, a stack of debris flow deposits that have come out of those steep ravines, sitting on top of what we've interpreted as an older soil. It has pine cones, or excuse me, it has cones in it and needles. It's a pretty interesting deposit. That's sitting on older beach deposits. Here's that rusty color, like you can see over here. And in another part of the terrace, we see bedrock exposed. So here's Lucky laying next to this nice cool bedrock on a very hot day. And here you can see the surface of the bedrock buried by older beach deposits. And this is significant because this surface is about 3 meters higher than the modern bedrock platform. We'll get back to that because that's an important part of our story here. So back to the landslides for a minute and some of the techniques that we've been using. This is the front edge of Terrace Site 3, which is right here. And in this image, with a few people for scale, you can see wood sticking out of these landslide deposits. This surface is that what we think might be a former soil horizon here, and then older beach deposits down here. On the right is a contour map on a LiDAR base map. And so these lines are connecting areas of equal elevation. We do these kind of maps so that we can really highlight the shape of the land. Where the lines are far apart, the ground is relatively flat. Where the lines are close together, then we're looking at very steep topography. And so along here is that former sea cliff that I pointed out in the Google Earth image. This surface here is the terrace, and then this is the beach itself, the beach slope. One of the things you can see really nicely in this image are these landslide headscarps that I highlighted on an earlier image with the red arc shaped line. So here's one, here's another, and we can also see benches in here within these landslides. But one other thing that you can see on this image, which is really cool, is what happens in these ravines. These are the steep ravines that I mentioned. And what we can see here is this circular feature, dome-like feature, half dome, that shows us the pile of debris material that has been washed out of the ravines. So these are called debris flow fans. And these are debris flows that have come out of this ravine. And we've heard a lot about debris flows because of all of the wildfires we've had in the area. Well, this is sort of the same thing. We've had a debris flow come down through this ravine and spill out onto the terrace and form this cone, inverted cone shape here. We've actually seen what these deposits look like and can say that those that are occurring today that are ongoing are very similar in composition to what we see in the front edge of the terrace. And we've been able to target some of the wood sticking out of these debris flow deposits and do some dating on those pieces of wood. This one here on the left happens to be a root that of a tree that was growing in that older soil horizon. And here's also the same root in this position. And what we found out with our radiocarbon dating is that these roots could be as old, date back to 1686, or they could be as young as dating back to 1928. It's a pretty broad range, so that wasn't a very satisfying set of data. Here's a large tree sticking out of a debris flow deposit with a tighter age range. So this tree died sometime between 1846 and 1913. So that's a pretty narrow band. That definitely post-dates the 1700 year earthquake. And then this tree here in the debris flow deposits has also a pretty big range of age. So what we've been able to deduce from this, plus other radiocarbon dating that we've done in the area, is we can say that landslides and debris flows could have started before 1686 at this location and continued until the mid-1800s. We can't rule out that the earliest slides were triggered by the earthquake in 1700. And again, that's really important to us because if we can find landslides that we can say may have been caused by that 1700 year earthquake in 1700, then we've opened up everyone's eyes to other places to look for landslides that might have occurred with that Cascadia earthquake, and also tells us of the possibility of having landslides associated with a magnitude 9 Cascadia subduction zone earthquake, which we suspect should happen. Okay, now, and in my abstract, I told you we were going to see a snapshot of a lot of different studies, and most of these aren't done. So here's another approach that we're taking. What you're looking at here in this image is a slice of the slope, like a slice of cake. This is the upland, here's the beach, here's the terrace, and here's the slope. And this is this cross section, we call it, taken through one of the landslides. And this is work that Elise Freeman did back in 2021. And she's showing us this pile of landslide deposits that has slid along a slide plane on a bedrock surface. And we don't know exactly where the slide plane was, but we're trying to get that figured out because we want to know what kind of landslides occurred on the hillside. And more importantly, what would it take to trigger that type of landslide? Could it occur with just increased precipitation, or did shaking cause the landslide? And so right now, this student, Caitlin Card, is going to be doing some modeling to try to figure that out. And here she is with Elizabeth Davis looking at one of the joint surfaces, fracture planes in the bedrock. We were out there taking some measurements to try to get an idea of how strong is this rock and how steep are these surfaces and could they be involved in the landslides. So everything we've been doing has been targeting the big question. Are all of these changes that we're seeing a result of uplift during the Cascadia subduction zone earthquake in 1700? That's really the question we want to get at. And how much of the changes that we've been seeing can we attribute to uplift versus other causes? These are not easy to answer. We're not working in a simple area for sure. Most of the models that have been constructed so far tell us that during Cascadia subduction zone earthquakes, subsidence occurs, the land drops relative to sea level. But we're asking, did the land uplift relative to sea level during an earthquake? That's not been documented yet along the coast. However, it could occur. And so let me take a minute and explain this image to you from Ian Miller. This is showing us where the shoreline is currently subsiding or uplifting due to the tectonic compression pushing the Olympic Peninsula up, right? So parts of the coastline are currently uplifting. Those are the warm colors. Parts of the coastline, we're not so sure what's happening. Maybe they're going down, maybe they're staying the same. And that's what this patchwork of colors is telling us. Models show us that areas that are currently uplifting tend to subside during these large subduction zone earthquakes. And areas that are currently subsiding tend to uplift during these large Cascadia subduction zone earthquakes. And this is important because it tells us it's possible that uplift occurred out there. We just have to try to figure out whether it did or not. Not an easy question. I have another cross section here for you. This one was drawn by Elizabeth Davis, and I apologize, I forgot to get her name on here. But this is the upland on the left, the land side, and on the right is the seaward side. And on the right, we're looking at a sea stack, and the dark color is the surface of bedrock along this slice across the beach. So here's the sea stack, similar to the one that she has depicted in this cross section. And here in the foreground, in front of the sea stack, is the modern bedrock platform. That's where bedrock is being eroded in a planar fashion at the current sea level. When we go to the former sea cliff and dig into the toe, we see a higher elevation bedrock platform. That's this surface here. This is the same surface that I showed you earlier with Lucky the dog laying next to it. This is 3 meters higher back here than it is out here. And this doesn't make sense to be a gradual erosion, a gradual surface slope, right? So part of our next effort is going to be trying to learn more about what's happening to this bedrock surface between the toe of the slope and out here at the shoreline. And we think that this is, we're thinking this could be our Rosetta Stone for being able to answer the question one way or the other. So let me now walk you through a possible model of that kind of puts everything together that I've been talking about. And so here we have another cross section. We have the upland on the left, the former sea cliff, and the ocean on the right. And the green is bedrock. And here's sea level back in time with a modern beach berm and a tidal marsh behind it, and then beach deposits here. So this is what this area might have looked like prior to any uplift, if uplift occurred. Then we have uplift, and what happens with uplift is the land is lifted up out of the water. You can also think of it as sea level dropping. In either case, it's a relative change. And so when that happens, that berm and that tidal marsh are now higher than where the modern waves reach. Okay, then as sea level continues to rise over time, which is kind of continually rising, the waves at the front edge of the water start to erode back into this hillside, because all of a sudden there's this land mass that has been placed in front of where the waves used to crash. So the waves erode back that bedrock surface, exposing that upper and older beach deposit, that older beach berm with those organic rich tidal marsh deposits in the back. This is showing us our former sea level, and this is current sea level. And after uplift, the waves start to build up another set of beach deposits, younger, or what we call our modern beach deposits. Then we had a landslide. And this is the former shape of the sea cliff here in this shadow. And the landslide fails and deposits all of this landslide debris across that uplifted surface and out into the water. And the water then has to work, the waves start eroding away the toe of these landslide deposits and eventually erode back to its current position here. And so this is possibly what we've been seeing out there. We've got this cap of landslide deposits. We've got older beach berm and beach deposits, buried, organic rich, probably tidal marsh deposits, bedrock exposed, and then a lower elevation modern beach. One scenario that best explains what we're seeing out there that includes this concept of uplift or land level change, land level rise during an earthquake. So all of this is really interesting, and let's bring this into a modern setting and what we think is going to happen moving forward. And I'm almost done here. I know I've been talking for a long time. But we also need to think about the implications of climate change. And what we know is precipitation intensity is going to increase, right? So more water is going to get on the hillsides that could potentially lead to more landslides. We expect to see an increase in wave power, size, and run-up, which could lead to more erosion. Sea level is going to continue to rise, and that increases the contact time between the waves and the toe of slopes or the front edge of the terrace, if we apply this to Rialto. All of this leads to more and more rapid erosion and more frequent landslides and debris flows. So let's look at the scenarios for sea level rise for just a minute here. And again, work was done by Ian Miller and the UW Climate Impacts Group. And if we look at the most likely scenarios that are currently being adopted, and we say, what's the most likely thing to happen? We see that sea level could rise 2 to 3 feet in 30 years. And that's this range right here. There are some more extreme estimates and some lower estimates, but sort of the most widely accepted, most likely scenario is something like 2 to 3 feet in 3 years. So that's a pretty serious amount of sea level rise that could have major impacts to the landforms that we see at Rialto Beach and all along our coastlines. When is all this going to happen, right? Well, we've got a projection for a significant sea level rise in 30 years. We think erosion rates are something like 1 to 2 meters per year. I'm sorry about mixing English and metric here. But, 3 to 6 meters per year erosion, and maybe that'll increase as sea level increases. We already see shallow landslides every few years out at Rialto, so there's no change there. But the much bigger landslides we think are less frequent. That's going to change with the change in climate. And we already talked about earthquake frequency, something on the order of every 300 to 500 years. So what are my takeaway messages for you based on this work that we've done? The first one that we've learned the hard way is that the data are disappearing because of all that erosion that's happening and all the changes that are occurring in that dynamic environment. Retreat rates might be increasing. If we take a 2 meter per year estimate for erosion, rates, then the terrace that we see out at Rialto now, which is where the parking lot sits, could be gone in something like 25 years, all things being held the same. The decrease in sediment supply to the beach definitely plays a role, but it's a complicated interaction. What's going to happen is erosion is going to change. It's going to transition from erosion at the front of the terrace to erosion at the base of the bluff. And so there will be bluff retreat of that upper sea cliff and more landslides. We think the fact that we found this elevated bedrock platform and elevated older beach deposits is more consistent with uplift having occurred. And we also think that some of the landslides that we've been working on could be concurrent with the 1700 Cascadia subduction zone earthquake. If there's uplift, then we have new land level change hazards to be thinking about, and new modeling to do on our coast. And certainly climate change is going to play a role and likely increase erosion. I have a lot of acknowledgements and they're important to me. So I'm going to take a moment here. I want to thank the North Pacific Coast Marine Resources Committee, particularly Tammy Picorni, for supporting our work and helping us with this project. Also, the 10,000 Years Institute, Jill Silver, has been amazing at supporting our research and brainstorming with us. At the Olympic National Park, Matthew Dubois and Dave Conca have been very supportive and helpful with permitting and providing information. John Riedel, along with Ian Miller at Sea Grant, but John Riedel formerly at the North Cascades National Park, really got us started out here. We've been collaborating with the U.S. Geological Survey, particularly Brian Sherrod and Jesse Pearl. We've had a retired geologist helping us out there on a volunteer basis, Jim Miller. All of our the former students who have worked out there, who have now graduated and gone on and are employed, their organizations have been very supportive to letting them return as colleagues working on this project. And there are many others that I should acknowledge, but I don't have them or the time right now. So with that, I want to thank you for your attention for this long talk and see if you have any questions.
Thank you so much, Dr. Troost. There is some questions in the chat, and I think it's been pretty cool to see how lively people have been engaging with trying to answer those questions. But I think I'll start with the most recent one and kind of move our way back. One participant asks, have you located where any landslides along the coast, any other places along the coast that may have been caused, landslides that may have been caused by the 1700 earthquake? To which someone else responded, many scientists have been looking up and down the Cascadia coast, but none have been that have occurred in 1700. And then there was a follow-up question. Then is it only conjecture that the Macaw village at Cape Alava was buried as a result of the 1700 Cascadia event?
You know, maybe somebody on here knows a little bit better than I do, but we do know that there have been some pretty big landslides out there, but we haven't attributed any to the 1700 year earthquake as of yet. I suspect they will start showing up with time, but not yet.
Okay, thank you. Another question. Let's see here, there's a couple coming in. Could the distance from where the tree that fell that had previously been standing, I think that was maybe Boris, have been increased by not only by erosion, but the water/tides moving the trees?
Yeah, I've wondered about that. It's like, in other words, has Boris sort of migrated down the beach, right? Down slope? I don't know the answer to that. Most recently, Elizabeth Davis was out there and we were finally able to see Boris's roots in these older beach deposits, but only a little bit. So there's definitely, it's an enigma. I don't know the answer. I
That's
wish I did. Yeah.
that's a good scientific response.
Yeah.
Do your I'm going to get this wrong, photogrammetry observations of land-based trees match the erosion rates seen in the beach-based ones?
No, they don't match well enough for my satisfaction. But we've only done a couple. And so we want to find more trees that we can track through back in time in air photos to get a better data set. Right now, the one that we do have gives us one of our higher erosion rate values. And so, you know, I'm a little cautious to say that we're looking at erosion rates on the order of 3 meters per year, because I just, you know, most of the data says that it's more like 2 meters per year.
Great. Has there been any measurement of sea level rise at Rialto or anywhere on the eastern Olympic Peninsula coast?
On the eastern, there have been. I would like to actually call on a friend from the audience, audience assist with this question. I don't know if Ian Miller is in the audience, but this is his area of expertise. And I think let's let him do this so that I don't bungle the answer. Thanks, Ian.
Absolutely, thank you. So yes, we have tide gauges located at Nia Bay, La Push, Coke Point, the mouth of Willapa Bay, and in Port Angeles, Port Townsend. And those are all essentially measuring sea level change. Some do it more effectively than others because they've been in place for longer time periods. And so the observations are mixed because land level change is different at each of those locations. But if we correct for land level change, so if we remove the land level change influence from those tide gauges, we find a sea level rise rate. So this is just what the ocean is doing in all those locations of roughly 2 millimeters per year or so. So we do see it reflected in those tide gauges.
Thank you.
Thanks, Ian.
Just a couple more here. Thanks everyone for your time. What are some safety concerns of camping at Rialto Beach in terms of moving logs, landslides, etc.? Are the changes in position of logs happening mostly in the winter storm months or year round? Are you able to measure it and see that kind of resolution?
You know, I think up until this year, I wouldn't have thought much of being naive. I wouldn't have thought much about safety concerns, but overnight we saw the tree that we call Vespa fall during not even that big of a windstorm. So safety concerns would relate to, or would hinge around those trees that are dying and those trees that are closer to the edge of the terrace where they're clearly being undermined by erosion. Those are the ones that seem to be falling more frequently. But it's definitely a concern for those people who are camping out there, because there certainly are a lot of them out there camping. And then the logs moving around, I'm going to do a phone a friend back to Ian because he's been looking at this more precisely, much more precisely than I have with respect to when are those trees moving the most.
Yeah, I mean, basically those trees are, you know, sort of in motion associated with high water events, which can happen year round, but tend to happen more in the winter time. And so it's well worth thinking about logs when you're traveling on the beach, anywhere on the Olympic coast and in Rialto as well. You've probably seen maybe a sign or a T-shirt that says beach logs kill, and they definitely are dangerous when they're in motion. So it's well worth thinking about that.
Indeed, some situational awareness. I see Steve Fradkin of the park says, and know your tides, know the storms, and also some situational awareness of where these falling trees or exposed trees are. So
I would add to that one more piece on the safety concern, not to mention the wildlife, which is a different topic, but there are also rogue waves that show up and catch you unaware. And we've had some of our team get wet before when they thought they were well out of tide range. So.
Yeah, don't turn your back on the ocean. And there are
No.
some big tides coming up, especially around the holidays. So something to be aware of. One more question, then followed up by a quick one. There are many great photographers in the area. Have you reached out to them? I've seen many photos of this beach in my short time here.
That's on my list. I definitely want to figure out how to reach out to the photographers. So if anybody has a great way to, sort of communicate with a lot of them in one short period of time, I would love to, because I do know some photographers who have captured changes in the sea stacks, for example, over time, and captured, been there when some of the sea stacks have collapsed. And that also speaks to the citizen science component that I think this project could greatly benefit from, is having citizen scientists involved in looking at and observing and cataloging their observations. So
Good tie in there.
yes.
Well, out of respect for everyone's time, I will, I think, end the questions there and just thank you again, Dr. Troost. As a relative newcomer to the area myself, I'm of course aware of Rialto Beach. It's a stunning gem on our coastline and a powerful place to visit. It kind of seems timeless, but you've definitely given me a new perspective on a very dynamic and changing landscape. So thanks for sharing. Thanks for uncovering some of the mysteries out there, and more to contribute to the ongoing drama out at Rialto. So thank you so much for your time, Dr. Troost, this evening. And to all participants, thanks for being here and for your continued support of Perspectives.